All right. So as Matteo mentioned, I'm going to be discussing a bit of a different type of topic for this event, and we're going to be looking at the kind of risk and how we can assess and map the risk of ground displacement for right-of-way infrastructure. So ground displacement is a global threat that is basically occurs in a variety of different parts of the globe. So if we look at this map here, we can see that areas that are medium to high risk cover majority of the United States, with areas of higher risk in California and the eastern seaboard, as well as in the central United States. And then we have, as I mentioned, global coverage of ground displacement, where it impacts a variety of Europe, as well as Africa, India, and in parts of China. So this is really an area that's impacting a variety of different types of ROW assets and infrastructure, as ground displacement is getting worse due to certain climate events. Now, ground displacement, as I mentioned, this is an area which has and can have both a impact on roadways, bridges, rails. As you can see here, it can be minor in terms of supporting identifying areas where preventative and road maintenance might be required, where it can also be used to identify potential precursors and risks to complete failures or collapses of things like bridges, as well as identify and prevent risks of derailments due to ground displacement activities and events along railway networks. Just to give you an idea of the kind of impact that this can have, because this might be a fairly new topic for certain people. If we look at roadways in particular, in 2021, or as of today, basically over 40% of the US road systems are in poor or mediocre conditions, and there's a $435 billion backlog for maintenance costs in order to bring up our road and bridge systems into a good standing in the United States. The challenge to this and the implications of this with regards to ground displacement is that these areas are more susceptible to cracks, fissures, and potholes as a result of ground displacement activities in the underlying geology. And the same thing is within Canada, and it's also across much of Europe as well. So we can see in Canada as well, we have 46% of our road systems, so I'm here located in Canada, are in poor or very poor conditions. And same thing, these are more susceptible to ground displacement activities. When we look at bridges now, often ground displacement and subtle movements of these assets can be a precursor towards a potential catastrophic failure of these different bridges. Now, this is even more important in the sense that 46,000, or approximately 7.5% of all US bridges, are structurally deficient. And basically, this impacts about 178 million different people passing by these bridges every single day. So this is a real risk that needs to be managed and monitored on an active schedule. And then same thing in the rail. The example I want to just talk about here is that there's a vast rail network throughout the world, but particularly in the United States, 160,000 miles, 21,000 miles of those are passenger rail. And same thing, these networks are, many of them are in less than great standings, where there's a $45.2 billion backlog for repairs of these infrastructure. But as you can see, it impacts a large area. Now, the question is how do you monitor all of these different types of assets or infrastructure networks span very large geographies? So the question is, how do you effectively monitor them and create a risk management or monitoring system that's cost effective? Now, some of those stats are obviously alarming, but it becomes even more concerning when we look at the impacts of climate change and the fact that this is accelerating and exacerbating certain risks within due to ground displacement for these types of right-of-way assets. So if we look at certain areas in the Arctic, now many of you who came from a geography background probably are familiar with permafrost and the impacts of permafrost. So if we look at the Arctic and subarctic areas like Alaska, we can see that permafrost, basically, as it's melting due to global or climate change events, this actually causes the ground to subside, and then this causes significant damage to pavement, to rail networks, and to a variety of different infrastructure within these that overlay these geologies. Now, right now, USGS is predicting or projecting about a 16 to 24% reduction in permafrost by 2100, so at the end of the century. And the cost of this in Alaska alone is going to be about $5.5 billion, as high as $5.5 billion by the end of the century, according to some models. Now, this isn't just a problem for the North or for the Arctic and subarctic areas. More temperate climates also have impacts and are going to be impacted negatively by climate change, and as a result, seeing increases in subsidence activities. And this is due to a different type of phenomenon as opposed to the permafrost melt, and this is due to something known as shrink swell. So shrink swell is basically the concept that as moisture levels change within clay-based soils or clay-rich soils, this can cause a uplift as well as subside. And as they decrease, or the moisture levels decrease, this can cause the clays to crack and break down, and which can cause sudden subsidence events, essentially where the pavement and the roads and railway networks can suddenly dip down and cause damage and require costly maintenance. So, as you can see in the UK, this is a study that was done by the British Geological Survey, and the UK alone, basically they're expecting to see a significant increase by 2070 in terms of the number of areas that are impacted. And often the problem with this is these are often in highly populated areas such as London. If we look at right now, just once again to give you an idea as to the kind of impact that this is, shrink swell is one of the, and subsidence in general is one of the costliest geohazards around the world. But in the UK, in the last decade, it's spent over $4.15 billion on repairs of infrastructures and properties as a result of this. Same thing if we look at what they're projecting in terms of a worst case scenario. They're projecting that by 2070, up to 10.9% of all properties and surrounding infrastructure such as roadways and rail networks might be impacted and at high risk to subsidence in these areas. So what we're basically saying is that we need to start to monitor and create monitoring programs and put these things in place so that we can begin to assess the potential risk and mitigate the damage by providing preventative maintenance and identifying where maintenance activities or further inspections are required to make sure that we don't have, one, to prioritize where maintenance activities are required in order to minimize the cost of these maintenance activities, but also in certain cases to prevent or minimize or mitigate the risk of a catastrophic failure. So one way of doing this, in a very cost-effective way of doing this, is to leverage a technology and a science known as Interferometric SAR, which uses spaceborne radar data. And basically this can allow us to monitor very large areas of infrastructure and these large networks in a very cost-effective manner. And we're going to talk about a technique that can be used in order to investigate this, and how this can be incorporated into risk management systems, into current asset management systems, in order to understand what potential risk and what mitigation activities can be done about it. So where does interferometric SAR fit? Before we go into a little bit more about the technical details about it and showcasing a live demonstration, I just want to make sure that the crowd and the audience understands that it's not necessarily a replacement, at least not today, for more traditional surveying techniques in terms of capturing ground movement information. And these techniques are things like GPS, GNSS ground stations. So these are fixed stations that are capturing real-time information, as well as manual surveying ground crews that'll go and survey basically anywhere that they're needed to assess. So it's not necessarily a replacement for that, but it's really more today a complementary activity that can help fill in a lot of the data gaps that are created by these different types of technologies due to technical and cost limitations. So just to give you a visual interpretation of this, let's imagine that we're paving a new roadway through an area. This is an engineering project, and essentially One of the ways that you can monitor ground movement in these areas to understand, to better understand and manage these types of assets is you could use things like fixed GPS and GNSS stations. The benefit of them, of course, is that they're capturing real-time information, real-time measurements. The negative aspect is that they're often plagued by large spatial data gaps or no data gaps, where there's just no information between these areas, and then in areas that are highly susceptible to ground movement, just to simply interpolate between these points may not be reflective of the reality around these locations. Now, often this is supplemented with manual surveying techniques where ground crews can be sent out to these different construction projects and different assets in order to fill in some of those gaps. Now, the benefit of that is that they can capture information anywhere they want, so they can fill in spatially quite densely. But the negative part is that it's very expensive to send these crews out. So really, they're only sending these crews out every few months, maybe every few years, depending on the kind of asset that they're particularly tracking. And in a lot of cases, for already post-construction activities, so existing roadways and current assets, a lot of them are not even being actively monitored at all today. Now, what we can do with this is we can leverage Insar technology to fill in those spatial as well as temporal data gaps by capturing regular revisits and dense measurements of these areas in order to fill in those gaps. And then what's great about the ground surveying and the GPS stations is they act as a calibration as well as a validation instrument to make sure that the measurements that we're capturing through spaceborne radar are accurate and meet the standards that are expected. So what are we providing? So we're providing basically the ability for you to perform historical assessments as well as actively monitor areas around and along your right-of-way assets, most specifically roadways, railways, bridges, but it's not limited to that. Those are more the right-of-way. It's also often used for utilities, pipelines, dam monitoring. So there's a lot of different types and properties, of course. So there's a lot of different types of activities outside of the right-of-way types of infrastructure and assets. What we're able to capture here is millimeter level, reliable millimeter level measurements. We can capture them for very large areas. We can monitor most locations on Earth. And this is made even more possible for certain types of infrastructure where roadways are particularly great for monitoring with Insar because of the return signal or response that we're able to get. We get a very strong response signal, and these are often known as what are called persistent targets or persistent scatterers. And then basically, we can also capture high density measurements that are updated on a regular schedule, and that interval is getting shorter and shorter. And we can also go back in time because we've had SAR sensors that have been collecting data that are capable of Insar, such as Cosmos SkyMed, that are capable of capturing SAR data that is viable for Insar applications. And we can go back basically decades with them in order to understand the kind of ground movements that have happened in the past around these different areas so that we can create and better model our engineering projects going forward. Now, there's a really interesting technique before I go into the demonstration is that we can also, we are sensor agnostic, and basically we provide these measurements and using our algorithms and our science, and we can provide them using open data for, which is often used for large area monitoring. So this is more to get a aggregate understanding or a general understanding of the ground movement in very large regions, whether it's a full city or an entire state, so on. And the benefit of this is that the data itself is free, essentially. So you're really just paying for the cost of the processing of the data. And this is capable of getting 14-meter maximum density. You're not always going to get that level of density of points, depending on the types of features that we're capturing and where in the world. But the benefit of this is it gives you a pretty good aggregate understanding or general understanding of the ground movement in different locations to see where you might want to perhaps spy commercial data and do what's known as a typic Q concept, where we can then say identify an area where it's more susceptible or ground movement is being detected, and then we can zoom in and understand and review buildings, roadways, and start to assess the risk of these types of assets in more detail. Where in this case, as you can see, we get upwards of 25 centimeters is the maximum density that's possible today. Now, if we just look at some of the specifications in terms of what's possible with these measurement points, is you can get open data where you can have max point density of, once again, it's 14 meters. We can get refresh rates of basically as 12 days and less. And we can do historical analysis as far back as 5 years. This is generally using a data source known as Sentinel-1, which is an ESA, our European Space Agency open data platform. Commercial data, there's a variety of different commercial sensors that we support. Basically, the highest of them can provide up to 25 centimeter maximum point density. The highest refresh rate today is 7 days, but once again, this window is very quickly closing. It's going to be probably within the next year or so where we're going to have same day measurements, especially as we're getting some of these new exciting constellations are stabilizing their orbit tubes, and they're going to be able to provide same day or even multiple day INSAR measurements. And then with these commercial sensors, we can even go back 13 even more years, depending on the accuracy requirements of the project. So this is an important variable in terms of, if you look at the risk management and asset management systems and different processes. So you might have different inputs into these different systems, like traffic density, what's the material that's being used, what's the shelf life, what's the age of the material, when it was saved for a road, when it was last paved, what's the weather and climate in these different locations. You'll have ground surveyor information that'll be introduced. A variety of the talks today, a lot of that data. So the conditions of the roads, the conditions of the materials, those can all be put as inputs into these systems. So what this is really, it's another valuable input that could be provided into these systems to understand what kind of risks and what kind of preventative maintenance activities can be performed in order to reduce downtime, reduce costs, and reduce and hopefully prevent loss of life due to complete failures. How we provide this information. So there's a variety of different ways. One is that we have an API, so an open API where this information can be directly fed into your systems. And it's done through, basically we can provide a variety of different formats. So either a GeoJSON format as well as CSV formats. And they can just be provided as new measurements, because this is a service or information as a service. As new measurements come in, those measurements are automatically, or you can have it set up so your API is automatically pulling those measurements basically from our servers. And then alternatively, we also have, this is what I'm going to show a demonstration of today, is a web application where you can log in to your area of interest and then essentially perform your own assessments, analyze the measurements, visualize the data in a web-based application, and then of course you can export them out afterwards to then incorporate them into your own system. So at this point, I'm going to leave the presentation and go into the demonstration here. So Insights, Catalyst Insights, this is the name of the solution or the information services web app that we have built in order to serve up the data. So as you can see here in this example, we basically have an AOI, which is the county boundary for Kings County. And this is where we performed our analysis for. So the way a user would leverage it is they would provide an AOI, and for the free open source data, that could be as large as 100,000 square kilometers, and it could be broken up into multiple AOIs. And then essentially we can perform or we will provide the measurements into these AOIs, update them regularly, and then you can perform or use a variety of the tools that we have built in order to perform different types of assessments and analysis. So as an example here, as you can see in this example, we have over 12 measurements captured over 6 months of Sentinel data. So we can see what what's known as cumulative displacement over these different dates. So we can change it so we have it for a different date here. I'm going to just put it for the last date. And what cumulative displacement really means is that basically it's the amount of ground movement that has occurred over a specific area since we captured the first measurement. So that's what we're basically showcasing or visualizing here right now. Now, as we zoom in and we look at certain areas, we can allocate, so we get the measurements, basically where the measurements, or we get the measurements over particular areas based on, and as you can see, it's not necessarily every single area. So certain things like vegetated fields, we're not going to get a lot of measurements for, and that's because they're not persistent scatterers, or essentially they are the measurements we'll get will not be reliable. So what we're delivering here and the points that you get are what's going to be reliable measurements that can be reliable up to a few millimeters, essentially. Now, how does this apply to right-of-way assets and right-of-way infrastructure? Well, one of the different applications is being able to allocate and assign risk to different types of infrastructure like road networks, where basically as we zoom in, I'm just going to let the data set load, or I'm going to zoom into a different area. As you can see here, it's loading. And then we can assign risk based on the ground measurements that were captured within a specific proximity of these road segments. And you can see that as I hover over these road segments, we can assign risk, and the user defines what is the risk table, essentially. So they will create based on the amount of movement in the area, whether it's low risk, medium risk, high risk. So that is all defined by the user. And then, and essentially they can use it along that way. I'm going to also just, for a moment, just look at a different area up here in this county. So this is where we actually have some areas of high movement. So we chose King County for our demonstration because it has a lot of ground movement, a significant amount of ground movement. As you saw on the map earlier, it's a part of California that is known to have a significant amount of displacement. And one of the reasons for it is because of the underlying geology, but also because of the aquifers are constantly being pulled on by the surrounding agricultural areas and the urban centers. And then so you're seeing a significant amount of subsidence as the aquifers are being removed, or the water is being removed from the aquifers. And then as it's replenished, you start to see uplift occur again. So some of the different capabilities we have with this, if we look at some of the roadways, when we zoom in just a little bit more, so you can see that we can look at what is the ground movement over time. So if I just select an area here and I can go around, say, a road network, say near this bridge over here. So we'll just zoom in a little bit more. So you can see this bridge. And we can see, I'll just make this a little bit bigger. So you can see the amount of ground displacement. So you can see what the cumulative displacement over time was for areas surrounding these types of infrastructure and these types of projects. So you can click on a variety of different areas where you can start to see what the ground movement and ground displacement that was being measured in these areas are. Now that's one important fact. Now, ground displacement is a natural phenomenon anyway, so we often will see some ground displacement occurring. Now, if it's occurring uniformly around an asset, that often is not necessarily a problem that we need to be concerned about. But when we have ununiform movement, that is where all of a sudden we might have significant risks to different types of infrastructure. So we have other capabilities and other tool sets in here where we can say, for example, draw profiles over areas. So once again, if I focus in on this bridge, we can draw profiles. I'm just going to zoom in a little bit more. So once again, we can draw profiles over this bridge, and we can see what the type of ground movement we would get. Just do it one more time. So now you can see here that there was two measurements that were captured along this bridge here, and they're very uniform. So really, there would be no concern for this particular bridge. Now, if we did have these measurements that were non-uniform, and one was significantly higher than the other, or moderately even within a few centimeters, that can be reason for concern. So just to go back, to the actual or going back to the slides and bringing this full circle in the story. So what are we really doing with Insar, and how are we able to capture those measurements, which once again can be used to identify where you might have or where you should send crews out for either further inspection of, say, bridges, or identify where preventative maintenance might be required. So we're leveraging a technology known as Insar, and basically, for those of you that are not familiar with it, it uses synthetic aperture radar, and basically we're capturing multiple images on different passes of the same area, where the sensor that is capturing it is in the exact same position as it was before. This allows it to capture what's known as a interferometric pair, where essentially in the first image, when we receive the return beam from that image that was sent out, let's say it's over here, this blue wavelength here, it's received at the phase is measured along the wavelength where it's received along that receiver. Now, when the second image is captured on a different pass, it's then, and say there's been a subsidence activity that's occurred, usually measured between a few millimeters and centimeters, we can now see that the phase has changed along this wavelength, and we can measure very precisely that change in phase, which then can be allocated and transposed to the ground displacement activity that's occurred, where we can look at it from line of sight, or we can also calculate it based on the vertical and also horizontal in certain cases. How are we able to provide reliable millimeter level accuracy? Now, that's another story. So that's based on a technology that we're leveraging. It's a hybrid approach that we took, which is well published and well understood in academia. And it's a concept known as SBAS PSI. So this is short baseline persistent scatter interferometry. Yes, that is a mouthful. And basically, we're leveraging the state-of-the-art Insar technique that is capable of, with the proper parameters and the proper inputs, is capable of consistently achieving millimeter level ground movement measurements. Now, the way that this works in a very, very high level is we're only capturing points over stable locations. Now, this is why it's such a great measurement system or tool for right-of-way assets, because railways, road networks, and bridges many of them are very, very considered stable points. So we're going to get a lot of points, a lot of measurements on top of these areas. What we don't want is features that are no longer, or that in one image no longer there, and also where we can't get stable points is in highly vegetated areas where the trees and the vegetation is moving too much, where the basically the imagery is no longer what's known as coherent. Therefore, the measurements really just can't be trusted. We deliver this, basically we have sophisticated rules, and we have an in-house team of Insar experts that are constantly tuning the parameters for different AOIs to make sure that the measurements we're delivering are accurate. And they're delivered with same thing. We have a team of Insar specialists that are supporting the quality assurance of the layers prior to delivery. Just to give you an idea of the kind of accuracy that's possible with persistent SBAS or SBAS PSI. So this is a study area that we did over San Jose, California. Basically, we used a commercial data set known as TerraSAR-X, where we're able to get 1 meter resolution or 1 meter max density measurements. And we had as our control was the UNAVCO GPS station, where essentially this is a fixed station, a fixed station that is capturing constant or real-time measurements. So we basically compared 20 measurement points over approximately 8 months. And what we were able to see here is that in blue, this is the daily average or the daily mean of the measurements that were captured by the UNAVCO GPS station. And then in orange are the measurements that we processed and measured using Instar Technology. And then this orange line here is the polynomial trend line that we created based off of these points. Now, as you can see, just from the visual comparison, you can see that there is a strong correlation between these two between the trend line and the real-time daily average measurements from the GPS station. And then when we compare the mean delta of the in millimeters between our measurements and the GPS measurements, they were approximately 3.6 millimeters. And then the max delta was approximately 8.5 millimeters for this data set. So basically, just to conclude here, what we're looking at is what we're able to provide is easy to consume mission critical geospatial data and intelligence. And we're doing this right now. We're providing this, the first offering around this service is around Insar Technology, which once again has many different applications, one of which is as a useful input to measuring and assessing risk of pre-constructed and post-constructed right-of-way assets, where we can capture millimeter level ground movement. We are able to deliver this through visual and analytical, a web app where you can provide visual and analytical interpretation. And then we can also deliver it directly through an API, or you can export the points through a CSV, so you can integrate this information directly into your systems, whether it's GIS, ERP, or another kind of risk management system or asset management system. So with that, I will finish things here and see if there's any questions. So thank you very much.
Thank you, Shawn. And I don't see any questions from the audience yet. But I was wondering about sort of the interplay between the satellite INSAR data and other sort of Earth-based sensors, and to use one to highlight areas that require more attention, and or vice versa. Sorry, do you mind repeating that question again? Yes, I was thinking that if you use the satellite-based INSAR in combination with various Earth-based sensors, you can maybe zero in on the more critical areas, kind of use one to highlight the areas to focus on with the other. And so any thoughts on that? Yeah, absolutely. So that's kind of the way that we see it right now, is that the Instar technology, while it's quite new and still there's a little bit of evangelism that's required to help people understand how it can be leveraged and make and provide people with the confidence about the accuracy. It absolutely can and be used with ground surveying technology. A lot of what I saw today in the presentations, where they're able to capture information about the road conditions and information about different types of encroachment, that I believe is just another source of input or another source of information into those systems to assess risk and prioritize maintenance activities. Right, and also using the automated feature extraction, figuring out where there are the most, the features that are most vulnerable to ground movement and the high risk points. Yeah, exactly. So I think it would be definitely used in conjunction with that. So if I saw a lot of the presentations earlier today were showcasing the automatic feature extraction of different right-of-way assets. So understanding, by having those features and understanding the kind of ground movement around those types of features, we believe can be a very valuable input. And once again, it's just understanding the potential risks and maintenance, or prioritization of maintenance of these different assets. A question just came in. What is the smallest feature you would feel is really as reliably captured using SAR? So basically, ground resolution from INSAR. Yeah, so the maximum point density that you can get from a commercial data today is about 25 centimeters. This is often due to government regulations. Now, you're not necessarily going to get
points or reliable measurement points for with a point density of 25 centimeters. Really, what this is looking at is if the ground is moving at an area, you want to look at proximities, I guess. So if there's particular types of assets that you want to, say, look at, such as hydro poles or power lines, you want to see what is the proximity of this measurement to those power lines. If it's within a certain proximity and that measurement or ground displacement is measured at a certain rate, then, or beyond a certain risk threshold, then you would identify that particular feature at risk. We're not necessarily going to be able to capture that individual asset, I guess, or that individual power line.
Right. With the proliferation of Earth observation satellites, all the CubeSats and the microsats and so forth, and you touched on this earlier, but can you say a little bit more about the interplay between what you can get from Insar and the visual, and
Optical.
the optical, yes, various optical instruments, and again, how one can help the other.
Yeah, I think there's a lot of complementary overlaps between, or complementary applications between Insar and optical imagery. I mean, Insar, what it's going to get you, it's going to show you locations where we and measure the amount of ground movement or movement of an individual feature, in a particular location. It's not going to tell you what that feature is or whether that feature is worth monitoring. So I think by tying it to visual or imagery and other assets, vector data, for example, to say, okay, it's within a certain, that measurement came within a proximity close enough to this particular asset. So, include that measurement for this asset. I think there's a lot of potential overlaps there.
Right. So, and I guess it's not just right of way kind of assets, but scattered kind of critical infrastructure assets would also be of concern. Everything from mines to, dams to power plants and things of that sort.
Yeah, and actually absolutely. So there's a lot of applications for managing. A lot of it is really within looking at the infrastructure itself. So monitoring dams. When it comes to roadways, a lot of what the applications and our customers are using it today for is looking at potential landfall or landslides around particular roadways. We have a couple customers right now that are looking at using it for identifying as a cost-effective method for identifying where there is a higher probability of potholes and I guess road pavement issues, so or poor conditions. So I mean, these are some of the areas that we're starting to see a pretty large uptick in terms of the applications for INSAR and ground displacement mapping.
Yeah, could you say just a little bit more about any particularly interesting application recently, or that have come across your
Yeah, absolutely. So we have a customer in Europe who is currently using it right now because there's a variety of different mines, coal mines in Eastern Europe that are being decommissioned, and over the many they've been mining in Europe for hundreds of years. So these collapses of these coal mines and these tunnels are causing property damage, infrastructure damage of roadways, and it's very difficult for the owners of the roadways, the municipalities and the owners of the property to be able to, prove that this collapse or this subsidence is specifically due to the mining activities that are happening underneath. So they're leveraging this right now as a tool, or I guess an input to see if when the subsidence happened, and then look at, is there any particular mining activities that happened underneath that likely could have caused that? So for insurance purposes and for recovery purposes.
Right, and there's also subsidence due to depleted aquifers in some areas, I guess, and you can have sudden sinkholes and things of that sort. So I don't know to what extent this can be a sort of an early warning system too.
Well, that's exactly it. So it could be used, so we can go back in time. So that's actually a challenge for a lot of geotechnical engineering companies right now when they're pre-construction phase of like roadways and property or different properties, is that they don't have any information on how the ground moves. So the only information they're getting is new information, and they have to make a lot of assumptions and model based off of that. Whereas with Insar, we can go back in time, potentially over 10 years, and understand the kind of trends that they are having in these locations, which can help give them identify the kinds of movements or what kind of engineering or how to model this better and protect the assets that they're building. But then also on the other side, we've seen a lot of municipalities that are wanting to use it to just actively monitor ground displacement within their boundaries or within their region, to just understand what is the impact of this ground displacement, and then also as a monitoring tool or monitoring information source for preventative maintenance and managing risk.
You know whether the success of what you're doing with this data is feeding demand for additional Insar capability in terms of putting more Insar sensors in the pipeline on upcoming satellites and so forth?
Oh, absolutely. I mean, Insar is definitely a driving force for more Insar technology and more satellites that are being launched regularly. I would say there's a number of main applications of Insar, but the two most prolific right now are coherent change detection. So you're seeing companies like Capella, companies like ISI that are going up and sending out vast constellations with the idea of getting same day revisit times for not only just the actual SAR imagery. And the benefit of SAR imagery in general is that you can see through clouds, you can see at night, so it's not restricted there. But basically also being able to provide this Insar data because of the millimeter level ground movement measurements that we're able to detect.